Hello, welcome to Basics of Noise and its Measurement. In the last lecture, we had discussed this concept of octave bands and explained that having and using these industry standard, internationally accepted definitions of octave band is useful, and it helps compare our results with other results which have been generated elsewhere, so that we have a common language for communication, at least in context of noise. So that's what we had discussed in the last class. Now what we will do today is continue that discussion forward, and specifically what we will do today is to learn how to calculate results for octave bands. Okay, so what do I mean by that? So we'll discuss octave band analysis, and what I mean by that is that suppose this is my time axis and this is my let's say pressure as a function of time, and when I take my data using data acquisition system and a microphone and all that stuff, I may get some curve. Okay, and what is my goal? My goal, so this is my input, and my goal is to report results in, let's say, octave bands. My goal is to report results in octave bands. What does that mean? What it means is that on my frequency axis, which will be in hertz, I will have specific center frequencies. Okay, and let's say this is 100, 200, 400, 800 or something, but these are my standard octave frequencies, and on y-axis I have to plot decibels. So actually, instead of, I will just call it FC1. This is second, FC3, FC4, FC5, FC6, and so on and so forth. And for FC1, let's say the value is this. FC2, the value is somewhere different. This is my value for FC3, that's my value for FC4, this is FC5, this is FC6. Okay, so then and I'm going to connect these with some line. So what does this point mean? Let's say look at this point A. So let's say the value of FC1 is equal to 100 hertz. For, we can assume that. So Fu is equal to 141 hertz, 100 times 1.414, and Fl is equal to 100 divided by 1.414, so it will be 70.7 hertz. Okay. Now, if I look at my FFT plot, so this is my time series plot. If I do its FFT, I will get some frequency spectrum. So this is my FFT plot. This is not octave band analysis. This is not that, okay. So in my FFT plot, what will I have? It will have some pressures, but they will be a function of frequency. And how do we get that? We use this DFT, we calculate xk, we convert that xk into the amplitude, right, by dividing it by n and then taking the magnitude of that. So that is the actual magnitude, right, because it will have a phase component and a magnitude. So what I am plotting is pk for different frequencies, okay. So I may have all sorts of values, and there will be thousands of values. Okay. In an octave band analysis, we are reporting results only at a very limited number of points, right. Here we have, if we have a total number of let's say 40,000 points, we may have tens of thousands of these values, you know, we may have thousands of these values. And let's say that this frequency corresponds to FC1, this frequency corresponds to FC2, this frequency corresponds to FC3, this frequency corresponds to FC4, okay. So when I do an octave band representation, I don't use this point to plot on this graph. This point A is not same as point B, okay. A is not same as B. That's not what I am interested in. What I am interested in is that so this is FC1 and there may be some right. So this may be FU1 and this may be FL1, okay. There may be FU1 and there will be FL1, and there is this energy contained in this whole band, okay. So what is our aim? Our aim is to somehow translate this energy in FL1 to FU1 band, convert it into some pressure number, and then plot it at location A corresponding to FC1. Understood? So if I just took this value which is at B and I plotted it in this graph, it would be totally wrong. What I have to do is I have to see this band, see what all points are there. Maybe there are 600 points, 1,000 points in that band. I have to take care of all those points. Somehow each point is associated with some amplitude for a particular frequency. So I have to somehow add up all that energy and convert that energy, so then I will get one single number. That number I have to be back calculate into pressure, and that is the pressure which I report here. Understood? That is very important to understand. So it is important because the method is fairly simple, but you have to understand what is happening, what is it that we are doing. So now I will explain you how we do this, and the method is very simple. So first, method. So first is get data PT. So this is pressure as a function of time. This is in time domain. Okay. This is my original data. And I don't lose this data ever because I will be processing this data. So I have to save a copy of this for second use and third use and 20th use. So I have to save this data. Second, now what am I interested in? I am interested in understanding how much energy is in this band. Okay. So what do? I use a band pass filter. This is again a standard method. I use a band pass filter. Corresponding to F L1 to F U1 band. Okay. What does a band pass filter do? So you can have actually an electronic filter, hardware. If you put it, then the only signal you will get from microphone will be for this band. But you don't want to do that, otherwise you will have to do this experiment lots of times. So you get your original data PT, and then there are digital filters. So you go to MATLAB or some software tool and you say that, okay, this is my original data. I am giving you this band FL1 to FU1. What is the value of this band? 70.7 to 141.4 hertz. Okay. So I give this to MATLAB and I say, please use this band pass filter corresponding to this band and give me the revised values of PT. Okay. Of PT, that is P prime T. So what have we done through this filtering method? We have eliminated all the energy which is below 70.7 hertz and all the energy which is above 141.4 hertz. How many points will we have? We will still have not 20, 30 points, thousands of points. Okay, but it will eliminate all the using this software methods. We don't have to discuss them. It will eliminate all the energy from corresponding to all frequencies. It will retain only that energy and those components which are for this band. Understood? Then what do? Now it is very simple. Fourth, now what is decibels? Now you calculate decibels. dB equals 20 log of 10 P RMS by P ref. So you have, let's say, 15,000 points. You take the RMS value of all these 15,000 points. Understood? And then you put that in this formula. So this P RMS is from this revised data. This is from revised data. So you get this dB. So then this gives you, so this gives you this value, A. So here you are putting in decibels, so here you get this A. So what have you done? You have right now done only for that band. Now you have to calculate for the next point. So how do? You go back, so you this thing PRMS, so you calculate dB for A, this is fifth. Then you go to the next point. To the next point, you again have to refer to the original data. You don't destroy that original data. And then what do? For the next point, your band will be shifted. So it will be 141.4 times 2, 282.4. And then again you apply the band pass filter. You have energy only for that. Take the RMS, plot it there. So when you do this octave analysis, you don't have a phase plot and a magnitude. You only get the energy, which is magnitude, right? Because that is what you cannot calculate phase, because all frequencies are clubbed into one single number. So there is no such thing as phase. It's irrelevant. So this is what you do. Okay? So here we don't use FFT in this context. If you use FFT and you pick up point B, this will be totally different, because this value will be extremely less, because see, the energy is distributed among thousands of points. So this value will be extremely small if you calculated decibels. What you are interested in is adding up all the energy in this thing. Okay? So this is how you do it. So it will be important to learn to go to MATLAB and explore what is the MATLAB, this function for bandpass filter, test, create an artificial signal. What you can do is y is equal to a1 sine 2 pi ft sine, and you put in all the frequencies, so you know how much energy you are putting for all the frequencies, and then you can put the filter, calculate what is the decibel value of that thing using this method which I am explaining you. So you will get one value, and then in another case what you do is you physically don't include all other frequencies but only those frequencies in that band, and then you calculate another value, and if you have done your math, they should match. So that way you can compare whether your octave band analysis numbers using this method are coming correct or not, whether you understand this concept correctly or not. Okay? So this is what I wanted to cover in this lecture, and in the class which will be tomorrow, we will discuss this concept of weighting. Okay? So thank you very much and have a great day. Bye.